Hello and welcome to the Bit Gardener webinar on dispersion. My name is John Kowalski. I'm part of the marketing team here, and I'd like to welcome you. Today's topic, dispersion deep dive. It says a deep dive into the pre-dispersion process. We have one of our resident experts here presenting, Mr. Andy Stummer. He's managing director of the BMA Goetzman product offering for us. A little bit of housekeeping. We are recording this, so immediately following, you'll receive an automated link to that recording. Feel free to pass it to colleagues, watch at a later date and grab any screenshots you need to. If you do have any questions after the fact, you can hit reply to any of the marketing messages you receive, and it'll be routed to my team, and we'll funnel it to the right person with the right expertise in your area. Also, this is a full hour or almost hour presentation, but if you do have any questions, we should have a little bit of time at the end. Just jot them down in the chat box. It should be located in the bottom right hand corner of your screen. If for some reason we do not get to your question, we will follow up individually and directly with you. So if something's on your mind, or if there's something we can help out that you're experiencing at your own facilities, or if you're just looking for information, let us know and we'll get that information to you. So Andy, how are you, sir?
I'm doing great. How are you doing, John?
Can't complain. All right, you ready to take it away, sir?
Yep. Thank you. I see we got a good number of visitors today, so welcome to our dispersion deep dive presentation day. So this is actually the first part of the dispersion process. So I think next week, John, is the second part. We're coming up soon after this one.
Yeah, I think it's in a few weeks. I'll post the link to register in the chat here shortly.
Okay, so that's actually then the deep dive into the milling component. So today it's about pre-dispersing and working with the dissolver and the Cowles blade. So with that, we going to do a little introduction first about who we are at the company and the relationship with BMA Goetzman, the company that actually makes the dispermats. We're going to then go straight into the dispersion process. And then what we're going to do is cover some of the different types of equipment that we can use in the lab, as well as pilot and manufacturing. You can see that right here really nicely. So the product line is really from laboratory scale all the way up to manufacturing. We'll talk a little bit about QC capabilities, and then also about our beautiful lab in Wallingford, Connecticut, that we have available for you to come in and look at the equipment and do some trials with your product. So with that, the company VMA is actually the manufacturer of the dispermat. So they own the brand name Dispermat. Company was founded in 1972, so just over 50 years ago, by Herman Goetzman, his beautiful wife up there. So they are still alive. And Herman actually is still visiting the company about once a week, just to make sure that things go well and that the designers are still following his design philosophy. So the company is managed today by his two children, Christian Goetzman and Martin Goetzman. They're both running the company. Christian is more on the sales side, he's the CEO, and then Martin is more on the financial side of the business. The relationship with BIG goes back all the way to the actually before 1988, in the early 80s. The former CEO had brought over some dispermats from Germany to our facility at BIG USA in Wallingford, Connecticut, where the additives group is located. And then they had some customers to come in and do lab tours, and they saw the dispermats. And a lot of the people that saw them were like, hey, we would like to also buy a dispermat. So in 1988, we signed an agreement with Mr. Herman Goetzman, the founder, that we would become the exclusive distributor for the product line here in the United States and Canada. So that goes back all the way to 1988. So the company is still in family hands. They have about 100 employees worldwide. And BMA Goetzman is known to build really high quality dissolvers, speed mills, all the different attachments, the basket mills, or some people refer them as immersion mills for the lab space, and then scaling them up all the way to pilot and manufacturing. So the picture on the bottom here is actually the very first dispermat that was built in 1973. And I've been with the company for about 20 years, and we still have customers that, believe it or not, are still using the original dispermat, the design anyways, from 50 years ago. The only thing that they replaced recently, about 10, 15 years ago, were the control box, but the motor and the stand and everything else is still in operation. So that really speaks for the quality of the dispermat brand. Okay, so here you see a picture of the facility in Germany. So the company is about 30 miles east of Cologne, about 50 kilometers. And they're located in a small town called Reichshof, Germany. It's kind of in the middle of Germany. The building in the middle, the addition in the back is new. And then they also added a second floor to improve their design capabilities and have more manufacturing and storage space. BMA is also known for being really flexible when it comes to different customer requirements, right? So everybody, especially if you think, there is a lot of new end-use markets like battery or fuel cell, for example, or the 3D print. So they're really able to customize their machines and make them suitable for all these new end-use markets. So about 40% of all the new equipment or everything that BMA builds is custom. And not only for the lab space, but as well as pilot plant, as well as manufacturing. And then, of course, we have a really good testing facility there for larger trials. We call it the tech lab, as well as a small lab to do small trials on benchtop units. So if you are in Germany or you would like to go over there and visit the facility, we'd be glad to have you and can even run trials on your products. Okay, so let's go right into the dispersion process. What are we actually trying to do here? So we want to improve our wetting. The most important part, obviously, is the invisible forces that they are holding our pigment or particles together. They're called Van der Waals forces. And these invisible, like electromagnetic forces that are binding these particles, we want to break up those forces. So that's really what we're trying to do, is just break up these invisible forces and reduce these larger particles, these agglomerates, and turn them down to aggregates, and then ideally reduce them down to primary particle size, which would actually happen when we are completing our milling cycle. That will result in improved color, better gloss, overall appearance is improved. Obviously, dollars are important to everybody. So the pigment efficiency is a really big one, because by reducing particle size, I'm increasing my surface area. That means in return, I can develop my product with less pigment quantity or other raw material. So that really helps us save money on the raw material side. And in turn, we'll get better product consistency, helps us improve our formulations, gives us also more consistent and even particle size distribution. And finally, when we go from the lab all the way up to plant and production, we're able to get really good upscale results when we do a good job dispersing in the lab. So if we don't do a good job pre-dispersing or dispersing, we're going to have issues with our color. We're going to have poor stability. Flocculation of pigments is a big one. That also has to do, obviously, with the type of additives that customers are using. So it's very imperative that you're using a good, additive in your formula to make sure that these pigments don't flocculate back together. This big USAs, very good dispersing agents, sagging, leveling, settling, as well as reduce gloss level or haze are some of the issues that come up, and then obviously separation of our particles. So it's very important that we look at the stability. So pigments in general require strong color fastness to reduce the fading over time. That's a big one. Obviously, brightness. This will give us the best color. Particle size. Basically, there is a rule of thumb. So the smaller the pigment particles, it will give us better transparency, better color, overall improved appearance. And then again, cost is a big factor because it allows us to use less pigment or other additive to ensure that we can save money for our formula. Viscosity, generally speaking, if our viscosity should be more on the lower end, that will give us improved particle size distribution and processing. So if the material is too thick, it's very difficult to use a blade to properly disperse it. It's just like the blade is kind of moving, in the middle, and then you have the product kind of stuck around the container wall. Of course, there's scraper systems and everything, but ideally we want to be on the lower end, kind of to low to medium viscosity, ideally. If it's too low, then we're going to have a difficult time putting in the right amount of energy to break up these particles and binding forces. So ideally, we want to look at something like 1,000 centipoise to about 3,000 is really optimum for a proper pre-dispersion. Okay, so critical here, we're really only trying to reduce particle. We don't try or break up these binding forces. We are not trying to destroy the particles. So the agglomerates, which are these larger clusters, we're going to turn them into aggregates, which are smaller clusters of particles. And then when we are actually milling, we're going to reduce them down to the primary particle size, which will be discussed in the follow-up presentation or part 2 of what we're talking about today. We're going to really dive into the milling component. And really shear forces are responsible for that separation. So by having a blade with teeth, we're able to put in or dial in the right amount of, tip speed and energy to really help us break up the van der Waals forces and reduce these particles. And then again, the additives play a critical role that they help us stabilize the particles once they are separated and are in a suspended state so they don't flocculate back together, especially when you're storing the material. That is very, very important. So here's just a slide showing you different types of pigments, what that looks like under a microscope. And ideally, we want to get down to primary particle size for the best optimum results. I really like this slide. It kind of shows you visually kind of what we're talking about when we talk about these agglomerates and aggregates. So you can see right there, the agglomerates are these larger particle clusters. So by using a blade in the pre-dispersion process, we are breaking up these clusters and reducing them down to the aggregate size. If we want to go down to primary particle size, that's when we need to do the milling or fine grinding. That would be that step. But today we're talking about how we get the agglomerates down to the aggregate level. So here we're also wetting of these solid particles, and it's the mechanical breakdown of the agglomerates down to the aggregate level, and ideally then eventually with milling down to the primary particle size. And then we want to obviously stabilize the particles with the additives. Kind of same thing here, but kind of more visual in terms of what happens when we use the equipment. So we start out with the blade, impeller blade or Cowles blade or dispersion blade. People have different names. we are using a blade with teeth. So here you have it. The cow's blade basically has teeth on both sides. By dialing in the right tip speed, which is about 18 to 25 meters per second, that is the sweet spot. And that will allow us to really break open these van der Waals forces and reduce these agglomerates and turn them down to the aggregate level. Once we reach the aggregates is when we start the milling cycle. And there are obviously different systems, bead mills, horizontal, vertical, immersion mills, which we will be discussing next time in more detail. But that's kind of like, in a nutshell, what that process looks like. So here is a visual, kind of a table or graph that kind of shows us kind of the sweet spot and at what point we are starting where the dissolver with the blade is most effective, in what range, and then what range we would need to start the milling cycle. So depending on the material, the formulation, we have a sweet spot from about 10 to 30 microns of particle size. That is the optimum range to work down with the dissolver. Anything smaller is when we actually would need to start the milling process. So if you're looking for something below 10 microns of particle size, or even go down into the nano range, as we see with a lot of products like automotive coatings or battery slurries or those products, then we really also need to take a good look at the milling technology and understand what works best for certain particle sizes. But remember, when we are pre-dispersing, 10 to 30 microns particle size is kind of where we want to go. And then that would be sufficient with the cow's blade. It's very difficult to go below 10 microns for most of the products just using a blade, because we only have a certain amount of energy we can put in with the blade and the teeth design. There's just a limited amount of shear stress, efficient shear stress to allow us to get down to the 10 micron range. Anything smaller than that is very difficult to achieve by just using a blade with teeth. We just don't have enough energy input that allows us to get any smaller for most of the products. So here you can see it kind of laid out, the dispersion process, always two parts. First, we pre-disperse with the blade. Again, remember, tip speed or peripheral speed, 18 to 25 meters per second, optimum. Anything slower than that, not really ideal. We are not efficiently dispersing. May take a much longer time to get to the results we want to get to, or we actually may never get there. So always look at the right technology that allows you to get to those speeds that are needed in the pre-dispersion process. So a standard mixer won't be able to get you there. It looks like a dissolver, but it's just basically a mixer. Even if you put on a cow's blade, if it doesn't get you to 18 to 25 meters per second, you are not hitting the ideal tip speed, and you will not get the results that you're looking for. You need to have a dissolver. So we have a variety of products for the lab, as well as pilot and manufacturing. We'll cover some of those later on in the presentation. Fine dispersing, milling, grinding is the second part of our dispersion process. You can see that there is 10 to 16 meters per second. The optimum rotor speed or milling disc speed is quite a bit slower than when we're actually pre-dispersing. But we also use beads. The beads are very important to give us the shear that we need to reduce these aggregates down to the primary particle size. There is also a variety of different systems that we offer or you find on the market. So we in 2 weeks, we'll look at the vertical bead mills in more detail, like those basket mills, as well as horizontal bead mills that are available for that purpose. Okay, so since we're talking about step one today, which is pre-dispersing, we need to look at a few things that are really important. We want to start out with obviously the right blade and container ratio, right? So if you look at that picture, the rule of thumb is about 1/3 of the diameter of our vessel should be the diameter of the blade. That's kind of the rule of thumb. However, because we're dealing with many different formulations and viscosities and also vessel sizes, we really need to adjust that depending on what we're actually producing. So let's take, for example, a 1,000 milliliter container. Keep in mind that we're looking at about a 50% fill rate, which is optimum. We can go as high as 70%, but then you really need to use a cover to ensure that the product doesn't spill over when you are adding all the energy and you're getting up to that 18 to 25 meters per second tip speed. It's quite turbulent, and you want to make sure that you are definitely putting a cover on there, not only for safety reasons, but also to keep the product inside of the container. So if you're looking at, let's say we are looking at a 1,000 liter container, optimum, obviously, we can go down as low as 30, 40, as high as 70 millimeters of dispersion blade diameter. So it's probably somewhere 40 millimeter would be kind of the sweet spot, depending on the viscosity. So if our viscosities are really thick, we want to increase the diameter of our blade. If the viscosity is on the lower end, we want to reduce the blade diameter. So we have a range from 30 to 70 with a 1,000 millimeter container. So just keep that in mind. The question comes up a lot is what blade size should I be using for my product? Okay, so the tip speed. So the good news here is on all of our new machines, except the LC. We'll talk about that in a little bit. We will show you the tip speed calculation or the tip speed value on the display. So you don't have to figure it out yourself. That's a really nice feature that's new. In the past, only our high-end machines had that capability. The new ones all show you the actual tip speed. But if you want to calculate it, so you basically have your diameter of your blade, you multiply that by pi times the RPM, divide that by 60. The diameter, since we're looking at meters per second, you always want to express in meters. So if you have a 50 millimeter blade, for example, you want to express it as 0.05, multiply that by, let's say, 5,000, and then times 3.14, and divide everything by 60. That will give you the actual tip speed number based on a 50 millimeter blade running at those RPMs. And then you can make adjustments accordingly. So if the blade diameter is optimum and you are too slow with your tip speed, then you need to increase the RPMs. If you find, okay, you may want to swap out the blade for a larger blade, then you may be able to hold the RPMs constant, just change the blade, make the diameter bigger, and that should also yield a higher tip speed. So again, on the new machines, it's automatically calculated for you. The only thing you have to do is enter the correct diameter, blade diameter on the control panel, and that will automatically then calculate it for you based on the RPMs that you're running. So it's a really, really nice feature. When we're pre-dispersing, we are also dealing with something called the donut effect, which is called that way because if we optimize our dispersion process, we're able to actually see a donut being formed inside of our container. That's what we want to see when we optimize our tip speed, blade to container ratio. Ideally, we like to see that beautiful donut being formed. And at that point, we kind of know, hey, we are doing a good job. We are pre-dispersing. We are de-agglomerating. We are on the right track. So that's kind of like the visual cue that we are getting when we are looking inside of the vessel during the dispersion process. What happens there is actually as the blade spins at those high RPMs, the particles hit the edges of the blade, and those sharp teeth really start ripping up these binding forces and separating those particle classes and reducing them to the aggregate level. What I'm missing on this picture, I didn't draw it, but I would have actually done the same thing on the bottom of the blade, because we have the same effect not only on top but also on the bottom of our blade. We are also shearing, and we are breaking up these binding forces. So I would have extended that picture, those particles down below the blade. Okay, so here is a real life example. We're running at an optimum speed of 21 meters per second. We're putting in 850 watts of energy, and we are looking at a really beautiful donut. Really good. Speed is good. Donut is there. We're putting in a good amount of energy. We are definitely processing the material. Usually within 15 to 30 minutes, we would have reached our goal of the optimum particle size prior to milling. Now, sometimes we're going to have an issue where we see something like this. So what's happening here? We are putting in 21 meters per second, or reaching 21 meters per second of tip speed, but we are really only putting in 320 watts of energy. So that means probably the viscosity of our material is not high enough. So we want to maybe change our formulation. We could also maybe adjust the blade to maybe see that we are putting in more energy, right? So energy is good, because energy is important to break up the binding forces. So if we're only putting in 320 watts of energy, but we're running a good tip speed, we really want to make some changes there to optimize that batch, and maybe by either adjusting the blade diameter, or by adjusting the formulation to maybe increase our viscosity, we're able to then put in more energy, giving us quicker results. But then we also have an issue. We don't have a donut at all, as sometimes you see here. We're putting in 900 watts of energy. 21 meters per second is optimum. But what's happening here is our viscosity is really high, which isn't really a problem, which can also give us good particle size reduction and breaking up of these invisible forces. But we are basically not ever going to see a donut, because the donut wouldn't be able to form, because the material is so thick that we are not able to actually see it visually. So we rely more on the data on the display to tell us, hey, we're doing a good job, we are pre-dispersing, and then maybe do a quick, dry sample, grind check with the grind gauge, giving us the indication, okay, we are moving in the right direction. But just because you don't see the donut in this case doesn't mean you're not de-agglomerating, okay? It just basically means that there is something going on with the viscosity of our material, because we have the 21 meters per second and the 900 watts of energy, which appears to be optimal. Okay, so to optimize our pre-dispersion or dispersion result, we obviously need to look at the time. So how long will that take us? So usually about 15 to 30 minutes is optimum. Sometimes we have seen it even go a little bit quicker, and sometimes it takes a little bit longer. But again, periodic checks, drawing a sample, doing a grind check will tell you exactly where you are and how far away you are from your goal. The donut effect, that visual cue, tip speed again, 18 to 25 meters per second, will be displayed on all the newer instruments. Geometric consideration, we talked about that. The ratio container to blade diameter. We want to also pick the right type of impeller disc. There's many different variants on the market. We have a whole range of them on our website, and you will find many more. If you do a simple Google search, there's a lot of custom blades. depending on your product and what you're trying to do. There's also different types of materials available, different coatings. So there's a whole range of different discs and material types that you can find. Mill base volume, about 50% is optimum. We can go as high as 70% and as low as 40%. You don't want to go much lower than that because you want to be able to still oscillate the blade up and down to make sure you get that sweet spot. And just sometimes, especially early on, you want to move the product more until it reaches that optimum level where you're actually seeing a donut. So you might want to dial it in, and 40% fill rate is really the minimum there. Pigment filler concentration, really critical. Okay, what is my loading? Try to optimize that, as we have seen on a previous example where we were putting in only 320 watts of energy, but we were running at 21 meters per second. Maybe that filler concentration or pigment loading was a little bit too low, so maybe we can increase it to have better pre-dispersion results. Temperature control is always important, not only when you're milling, where it's absolutely critical, but even when we are pre-dispersing, we want to make sure that we have some sort of a cooling mechanism, usually a double wall container with cooling jackets, and the chiller will be optimum. We have some customers that try to do it in an ice bucket. We don't recommend that at all because there's really no way to stabilize the container all that well. So always try to be safe and maybe use a chiller. We work with Chilabo. Chilabo is our partner on the chiller side. So if you looking at purchasing equipment, we can match up the right chiller to the dissolver or dispermat that you might want to purchase. And then again, additives are so important to help us wet out the material, give us a better dispersion result, and then stabilize the material before we actually start the milling process. So some key takeaways here: using a dissolver, or some people refer to them as the high-speed mixer. We are able to put in a limited amount of energy because we are only really working with a blade and teeth. So that limits the amount of shear force we can put in. We don't have beads to work with. In this case, it's the de-agglomeration stage, so the first step in the dispersing stage before we do the fine grinding. We are not going to reduce the particles down to primary particle size using a blade. So this is strictly only to de-agglomerate these larger agglomerates and turn them down to the aggregates. But it is critical. It's an important step to do the pre-dispersion first before you're milling. We have some customers that ask, well, what happens if I go straight into a medium mill? Well, you can try, but the problem is, or going to be, if let's say your starting particle size is 50 microns and you have a mesh size of 0.5 in your basket mill or your vertical bead mill like an APS, you're going to clog the screen. Or a horizontal bead mill, if the particles are too large, they're going to, sit there at the end of the back part of the milling chamber, not able to go through the dynamic gap or the screen. So you're going to clog up your mills. So it's very important that we pre-disperse first before we actually starting the milling process. And then obviously we talked about that earlier. We're going to have limited color strength, limited gloss, haze. All these issues are going to pop up if we are not properly using a dissolver. Then bead milling, obviously, the second step, which we cover in more depth in a couple of weeks. We're going to be able to put in a lot more energy. We're using beads, we're using milling discs. This really helps us to break down the particles or the aggregates down to primary particle size. Some cases, we work with customers that need to be below 50 nanometers, which is achievable with the right milling technology. And that really will give us the best product characteristic in terms of particle size, color, transparency, particle size distribution, and so on. Okay, so what does a laboratory dissolver look like? So here is a great example. So that's kind of like our flagship model here, the AE. That's a laboratory scale model. Gives you all the control options that you might want to have, especially if you're trying to track the data or if you're upscaling. The equipment, very importantly, has 3 different safety features that are a part of the unit. So number one, all the diplomats have what we call the working area safety threshold setting. That means that this is really important when you're pre-dispersing. You never want to have a blade spinning outside of the container. So for that reason, we have a setting called H1 and H2. So H1 is basically the lower threshold inside of the container that kind of stops the blade from going below H1. So you'll never run into the problem where you lower the blade to the point where it hits the container bottom. It would stop at H1. So you can set that prior to you starting the dispersion process. So usually the H1 value never changes because containers usually have the same thickness, especially in the laboratory space. So you're probably going to be about ½ an inch above the bottom. So you're going to lock H1 in and never changes. But H2 will change, and that is the upper threshold. So if I'm swapping my 1 liter container up to a 2 liter container or a 5 liter container, the height of my working area will change, right? So I need to change the H2. H2 is the upper threshold, and basically that means that once I set H2, the operator will not be able to lift up or raise the shaft up beyond that point, H2, while the blade is spinning. So it would automatically stop at that reference height, and then you have to power down the machine for you to be able to go above that threshold setting. You can freely move in between H1 and H2 and oscillate and do anything you want, but you'll never be able to find the blade spinning above the H2. If for whatever reason somebody were to start up the dissolver and the blade was outside of the container, it would give you an error message on the screen and tell you that you are outside of the working area. Therefore, you have to lower the blade to go between H1 and H2 to actually be able to power on the machine. So that is a really important safety feature. The second safety features our diplomats have is called the container clamping system. That ensures that the container is always perfectly centered, so the blade will not hit the container sidewall, and that you're always operating with a blade in the middle of the container for an optimum dispersion result. If it's cockeyed or it's off center, that will not give you a really good, repeatable dispersion result. So having that a container clamping system allows you to always optimize that. And that wheel right there on the right side of the machine, that is actually used to tighten the container clamp or loosen it. So there's a sensor back in here that measures the pressure and ensures that the container is always fully clamped. If for whatever reason somebody were to open that during operation, the machine would automatically power down and you wouldn't be able to run it. And then we have a third safety feature, which is our shaft guard, which you can see right here. There's a thumb screw. So you can actually open that up and then slide that up and down depending on where you are with your impeller in the container, the height, and then you make adjustments to make sure that there is no spinning parts outside of the container. Lab models can go as high as 20,000 RPM. Probably you're never going to get up there that high, but they are capable. The beauty of a dispromat is the accessibility. So you're able to buy different attachments like a basket mill, a vertical bead mill, a vacuum system, a wall scraping system, or even a rotor-stator. These are all attachments that you can purchase and they will fit right onto the machine. So you wouldn't, if you want to do milling, you can do that with one machine. You wouldn't have to go out there and find now a bead mill because you need a second device. No, you buy the attachment and now you're milling with a simple laboratory dissolver. That's the beauty of the Dispermat. Not only for our lab space, but also pilot and manufacturing. So the dissolver, this format will function as a homogenizer, as well as an emulsifier or disperser. So you see there's all these different attachments, rotor-stator. You can use them with the basket mill or just adding a milling disc. You can use them as a mixer. You just put on a butterfly or propeller blade. So you have various options on how do you want to use the machine outside of dispersing. So that picture here is really nice because it kind of shows you the idea behind it. So you have your dissolver in the middle, and then you have all these different accessories that you can purchase and fit onto the machine and make it very versatile that way. All right, then just want to go through a couple models here. So we have the economy line, which is the LC. It's a very simple model. That's the only model now that doesn't show you the tip speed. It basically is just a simple dissolver. Motor design is all the same across the board. So you're still getting a brushless step motor. If you have worked on the Dispermat before, you would know that they're the quietest machines on the market. There's nothing like them. You can run them at full speed and hardly hear the machine. High quality build. Basically, the LC will give you a speed indication, a timer function, but also you have the modularity so you can add different attachments. CV3 Evo, brand new, was introduced this year, replaced the CV3 Plus. Beautiful laboratory model, gives you all the functionality that you would expect from a Dispermat, plus the tip speed on display, the amount of energy you're putting in. It'll give you a torque value, which is kind of an indirect measurement of your viscosity, a product temperature. It'll also has a timer function. So you have really everything that you really need to operate in R&D, as well as upscaling that to a larger production unit available. There is a basic and an advanced model. The advanced model even has a scale where you can weigh out your raw materials next to the dissolver, and then it'll show you the weight actually on the display right there. Again, fully modular, giving you the ability to add all these different attachments we talked about to make that a truly versatile piece of equipment. CN, bread and butter instrument here at BIC, as well as for a lot of our customers. It's going to have a new control panel this year, also giving you the display, the tip speed on the display. Beautiful machine. Again, awesome for the lab. But if you are interested in using the same technology for your pilot and small production, and then you can stay within the same family. And there is a CN ranging all the way from a CN10 to a CN120, giving you that full flexibility of doing larger product volumes, yet staying with the same model type. Here's an example of the pilot scale CN model. So if you were to use one in the lab, there wouldn't be a learning curve if somebody were to say, hey, we want to do now, 10 gallons or 15 or 20 gallons. You just buy the larger model, and then people be able to operate it exactly the same way. Then we have the AE. That's the new one, premium model here. You can see it fitted with a basket mill attachment. That's really the best Dispermat that VMA has to offer. High-end, able to track the data. You can create lab reports. It has a feature called diagram. So all these indices like speed, energy, torque, time, temperature will all be displayed in a graphical interface on the screen in form of a trend line. And let's say you step away for a few minutes or half an hour because you have a phone call and you come back, then you can just take a quick peek at the diagram and you can see immediately, hey, was my dispersion process linear? Did everything look okay? Were there any spikes while I was gone? Did my temperature all of a sudden go up? Did my torque go up? Did my energy input change? What happened to the viscosity? So this is a really easy way, the quick way of seeing, hey, what happened or what is happening during the dispersion process. And then, of course, being able to export the data into an Excel format and create a lab report is really, really cool, especially if I want to go and scale that up to pilot or manufacturing. Again, AE premium line in pilot scale, same philosophy as with the CN, except with the AE I have that data tracking capability and creating those lab reports. All of the models at the AE and the LC are also available in explosion proof. So if you're running solvents or anything they like, we have that capability as well. Production scale, dissolver right here is the Dispermet SC. The beauty here is that you can also convert the Dispermet SC in a production volume capacity over to a basket mill. So this or rotor-stator. So you're not only buying a dissolver, you can also future-proof the unit by getting the DL shaft, which is the quick change system, and also utilize it as a basket mill in the future. So you do not need to buy an extra machine to mill your material, which makes that really, really efficient. And also from a maintenance perspective, easy to handle because I have one machine rather than two machines that do different things. I can do everything on one machine. So again, explosion-proof models are available, different container sizes. So really, really beautiful system for somebody who wants to manufacture larger batches. And even a vacuum option is available. People sometimes want to draw out the air bubbles. So you're able to do that very efficiently with the vacuum add-on. As you can see right here, allows us to eliminate the foam, put in more energy because the air bubbles function as like tiny little air mattresses and they impact the shearing. So by removing them, we're able to put in more energy, giving us, a better efficiency during the dispersing or milling process. And that will give us a better product. Some people like actually to have an extra port for nitrogen or argon. So that means that they can have a blanket. And that would also be an option, especially with the vacuum system. Okay, these were just some different models. We do have on the AE model, we have the ability, we'll get into that in a moment, the software add-on, which is called WinDisp. The display here on the actual AE unit will look exactly like the one on the left. And for production purposes, we have a more crude display, just giving you the important information in the manufacturing world. Also, the operators, don't, have to be very careful touching the buttons and so on. So this module on the right or control panel is really designed for the manufacturing. One thing I want to point out from a safety perspective there with the manufacturing units, when you lower the shaft, all the shafts have a guard or a cover on them. So you're able to lower the cover or the shaft by having both hands on the control panel. That means you see on the bottom where the up and down arrow, that's raising the shaft. So basically you have then to turn it with one hand and also turn with the left hand the knob on the left. So both have to be turned simultaneously. Otherwise, you will not be able to lower the container. That ensures that no one can have one hand inside of the vessel and now they're getting squeezed by the container cover, which would be terrible, right? So that's another safety feature that we put in place to make sure nobody walks away with broken fingers. Control panel on the left is the AE panel, so AE C controller. So here we have our speed 5,500 RPMs, 238, 80 watts of energy, power input, torque value 4.1. The tip speed we talked about 25.4, temperature 42 C. You can change that to Fahrenheit. You can also change the tape speed to feet per minute if you prefer that over meters per second. Also, the timer function right there, H1, H2 on the display, so you can set that digitally. You just position the blade at the exact height and you push H1 and H2, and that locks in those values for the working area safety setting. We have an optional light source. Some people like an LED light integrated in the cover, so you can turn that on, or a wall scraper, or so on. So all these things are optional. Okay, then we have a PLC controller for the manufacturing machines. Some people like to integrate a dispermat into their workflow. So having the ability to program it yourself or put it on a load cell to weigh out the material on the machine. So that would be an ideal solution to get a PLC controller to customize your own process. We have the ability on the AE to do what's called a net power calibration. Basically, before you are running any material, you can set the machine to an absolute zero value point. That means we are not including any energy that the machine uses to operate itself. Obviously, without product, the dissolver, when it's spinning, it already needs energy to move the blade. So by having a net power calibration, we're able to exclude that from the calculation and really give you a zero value. So you would know the amount of power that you're using is directly reflected, a reflection of your product, and no machine input. So some people, especially in R&D, want to have exact numbers. So the net power calibration is very important. We have WinDisp. Personally, the WinDisp Lite is good enough that this is the full-blown version, gives you the ability to control the dispermat from a laptop. It's, in my opinion, dated. Obviously, you can see the GUI. They're working on an updated version, but I believe that having the ability to port all the data over to Excel satisfies 90% of the customers. So if you really want to have a specific software, then the WinDisp is available, and we can help you install it. Again, this is an older software, but they're working on updating that to all the new machines. I don't have an ETA, but it's work in progress. Lab space for doing trials and experiments. This is in Germany at the headquarters. So if you have a colleague over there or a sister company, you can always give us a call and come and visit. We'll be glad to work with you and your materials. We have also a beautiful lab in Wallingford that has a lot more capability that you see here on the picture. We have a new AE6. We have a SL25, which just last week we put in a new dispermat DL with vacuum. We have all the different basket mill attachments, so rotor-stator, so anything that you want to do, we have all these capabilities. So if you're interested in coming and visiting us in the lab, be our guest. We will not charge you for a visit or even a day in the lab with you. The only thing we ask that you pay your way there, and we will provide lunch and dinner. So that is on us. So it's a really good facility. You'll be walking away with a lot of good data. You learn a lot being up there, specifically how the dispermat will help with your formulation. We can provide upskill support. The beauty of it, that it's with BIC USA, is that we will have a live chemist supporting any trial that will help us make formulation improvements if they are needed, give recommendation on the right dispersing agents or defoamer. And that really shows that we don't want to be just a hardware provider, but we really want to sell you the complete solution and support that you wouldn't be getting from anybody else at that scale. And then if you just want to come by and look at the equipment without running a trial, we can also set that up. We're glad to have you and just basically check out the equipment or even do some training for your folks on the equipment. So I think with that, we're exactly at 55 minutes, and that concludes the presentation.
Good job, Andy. Right on time there. That's a lot of information to go through. And like I said at the top of the hour, you're going to get the recording of this. So you can watch it, pause it, take screenshots, whatever you need. I think we have time for one question. Cowles blade / disperser versus rotor-stator versus caddy. What are the pros and cons and thoughts about those kind of three systems?
So the Cowles blade, I would say, is the universal tool, right? I mean, you're really, if you're starting out the process, ideally you want to start adding everything, wetting out your materials. So the Cowles blade is really helpful doing that. And of course, because of the teeth, it really will help shear down the material. Depending on what is your question or where do you want to go, right? The rotor-stator is a really excellent tool to replace like a milling system. If you want to go very small particles, it's also used as kind of an emulsifier. So historically, the application was different, right? So rotor-stator was mainly used for, let's say, developing a salad dressing. Oil and vinegar incompatible. So I would use a rotor-stator to really blend them together as efficiently as possible. Better than I can do with a Cowles blade. But because of these new designs in the rotor-stator and the gaps have changed, the edges are sharper. Now people have actually found out that they can use for certain milling applications a rotor-stator just as efficiently as to be able to use a medium mill. We have seen it for some really cool battery applications where somebody, instead of using a medium mill, now to use a rotor-stator. Of course, with the rotor-stator, it's important that you're keeping the viscosity on the lower side, right? So if the material is thick, it's not really conducive to those viscosities because the rotor would just kind of sit in the middle, the stator, and the rotor would spin, and it wouldn't really, push the product through these gaps and teeth. So it's important that you have low viscosity. The lower, the better when you are using a rotor-stator. But it really depends on the formulation and on what you're trying to disperse or even mill.
Yeah. Great question, Julio. If you want to explain and go deeper in that, just hit reply to any of the marketing messages. We'll get it to Andy and his team and get you an answer back based on your specific application. So with that, I'd like to thank everyone for joining us. We had a fairly big group today, so it's great seeing everyone out there wanting to learn about dispersion. Also, check out the link I put in the chat for part 2 of this, where Andy dives deep into the milling portion of this.
Next in 2 weeks, right? So
the 18th of October, so about 4 weeks away.
Okay.
So we got that coming up. And if you have any questions or anything specific you want to make sure Andy covers, you can, again, hit reply to any of the marketing messages, and I can route it to Andy and make sure he incorporates that into his presentation. So Andy, thank you as always. Great stuff. Lots of knowledge there. So we appreciate your time and expertise. Everyone else out there, have a great rest of your day, and thanks for joining us. We'll see you next time.
Everybody. See you soon. Stay safe.